Hi everybody, hi, Mike here. I'm here to talk to you about titration curves. And before we get along with this real short video, I want you to go and find the handout under Content, Exam 3, where there's titration curves. And let's turn to the page with the curves on it. Specifically, we're going to talk about that guy, the one on the left. That is a titration curve of a strong acid. And just for making things simpler, why don't we just go ahead and say that that's HCl. Matter of fact, why don't we say it's 0.1 molar HCl and 25 milliliters of 0.1 molar HCl. Now back to Gen Chem 1, you could figure out that those two would completely neutralize each other at 25 milliliters because they're both monoprotic acids. One's monoprotic, an acid, and one's a monoprotic base. And you'll notice here at the equivalence point, the curve has a different shape. But let's talk about what that is. That would be when the number of moles of HCl is equal to the number of moles of NaOH. And at that point, you don't have either HCl or NaOH. You've got NaCl, which we've talked about is a neutral salt. Now let's talk about why the curve has its shape. First of all, when we've added nothing, we know that 0.1 molar HCl will have a pH of 1.0. Now, think about this. As we add moles of NaOH, they're going to convert the moles of HCl to moles of NaCl as the H plus and the OH minus neutralize each other, right? Back to net ionic equations. H plus aqueous, or H3O plus, whichever style you want to think about it, goes to make water. So as we proceed along this graph, the pH will go up. How come it doesn't go up by a lot? Well, think about, like, what if this acid was like a rich person? Picture in your mind a rich person. Could be anybody else. It's your fantasy. What if you were to take every minute $1 million away from this rich person? Well, rich person would be rich for quite a while if it was Bezos or whoever. But then after a while it starts making more difference. Remember, pH is logarithmic. So let's get to the point where a rich guy, make it a guy, now has only $1 or $2 million to his name. Now you take away $1 million, that's starting to make a big difference, to the point where at the equivalence point there's always a huge change in pH with very little change in volume. And of course all this stuff is colorless. HCl is colorless, NaOH is colorless, so we need the help of an indicator. And the indicator has to work in a range a couple pH points away from the pH of the equivalence point. You probably recognize this titration, you've done it before, and we used as an indicator phenolphthalein. And actually we would stop right here, but in experiment 9, we kept on going to show you that there's a full curve to it. So let's talk about what an indicator is and why we can use certain indicators to determine when the equivalence point is, because we don't always have a pH meter at our disposal. Here's how an indicator works. Indicators are actually acids themselves, and they have an acid and conjugate base form. If we take phenolphthalein, which by the way used to be the active ingredient in X-Lax, but I will not go on a tangent about that. It turns out that the acid form in pH less than pH 8.3, so we'll call this the low pH form, is colorless, but when it loses an H plus, the bonding changes. That changes the wavelength of its absorption, and in solution it occurs pink. That happens at pH 8.3. Now let's go back to our titration curve and talk about why that's a good indicator to use with the titration we've just mentioned. All right, back to our graph. I've gone ahead and I've made an X where pH 8.3 is. Remember, you'd have the NaOH, the strong thing in the burette, and you'd be chugging along, adding a drop at a time, and you'd say, well, hey, what about that indicator not changing perfectly at the equivalence point pH 7? Well, we can get away with that. Look how steep this part of the curve is. That whole 2 to 4-fold pH change might have been a fraction of a drop. I mean, how many times have you gone over the endpoint and gone past and it was a little too dark pink and that was only 1 drop past? That's a 20th of a drop, or of a milliliter, 1 drop. What if this could be only a fraction of a drop? So it turns out we can use anything in this range, a couple pH points to each side. So I want you to flip over your handout and take a look. There's a graph, or there's a chart of all sorts of different indicators. And so we could have actually used, say, anywhere from methyl red all the way up to phenolphthalein for this strong acid, strong base titration. As a matter of fact, if you look below that, they illustrate that to you. They show you that phenolphthalein changes right about at the equivalence point pH, or the volume of it, 25 milliliters. So does litmus. So does methyl red, for that matter. All right, let's talk about another kind of curve where we replace what's in the flask with a weak acid. And this kind of gets to drone on. So in the meantime, let me go show you my turnips. Check it out. Those are turnips. All right. And this is so to keep the squirrel out, because he wants to eat them and stuff. That's going to be beets. That bed is full of what we call in science horse crap. So always good to have a horse crap friend. She makes me lots of, well, she don't make the horse crap. She just, okay, let's go back inside and talk more about titration curves. All right, let's talk about a titration of a weak acid with strong base. So NaOH, same kind of situation. What if we had 25 milliliters of 0.1 molar? I can kind of tell this is acetic acid by the equivalence point. But if you had, say, acetic acid at the equivalence point, this would be completely sodium acetate. So neutral ion sodium and conjugate base of a weak acid, acetate ion, and that's why the pH point isn't at 7 for this. Unlike NaCl in the previous example, this is a alkaline salt, and so you could look, this has a Kb equals Kw over Ka, 5.6 times 10 to the minus 10. I happen to have remembered it. So phenolphthalein would be a perfect candidate for an indicator here, and so would anything that goes on up to about pH 11 and pH 7. But now methyl red was suitable in the last example, but methyl red changes around pH 5 or so, and so that would not be a good indicator because it's not close enough to the equivalence point. Let's talk about this. 12.5 milliliters, which would be, if this was the equivalence point was at 25 milliliters, that's called the half titration point. That's at the point where pH equals pKa. Remember the good old Henderson-Hasselbalch equation? pH equals pKa plus log of acetate concentration over acetic acid. At halfway to the equivalence point, these would be both the same value. Whatever x is, depending on the volume of the original thing, that would go completely to 0. And so that's what happened in our Ka experiment. We took a completely titrated sample, poured it into a completely untitrated sample, and you had your buffer solution. By the way, you'll notice this starts at a lower or higher pH because it's a weak acid. So even though it's, say, 0.1 molar, pH is going to be much greater than 1. Okay, guys, that's enough for today. More in the next video. Here's what I want to tell you what's coming up. What if we switched it? What if we did a switcheroo and we put the base in the flask and an acid, and we put and titrated NaOH with HCl? What would that curve look like? And what if we did the same thing with ammonia, which I believe is actually what you did. So if we took a weak base, titrated with a strong acid, what if an acid or base had 2 H pluses and they came off one at a time. What would that curve look like? All these questions will be answered in the next video. Take her easy, folks. Hang in there, stay healthy, and practice safe science. Bye.